So we have seen how the Runge-Kutta method can be derived, and if we take from the Taylor series accuracy up to third order, we managed to get the midpoint method, and although I did not show it, it is also possible to recover the Hume's method from the second order Runge-Kutta approach. So what if we want a numerical scheme that is even more accurate? What if we want to take up to fifth order accuracy? If you want to take up to fifth order accuracy or order H5, then you will need to consider terms up to the fourth order derivative in your Taylor series. So in this case, let's say we want up to order H5 accurate. It means that you will need to consider the terms yt, y prime, y double prime, triple prime, and the fourth order derivative of y. So using the approach that I've shown to you for the second order Runge-Kutta method, the derivations are going to be a lot more complicated, a lot more tedious, but you should be able to come up with expressions for how to approximate your y double prime, y triple prime, and the fourth order derivative of y. Okay, so it's not necessary for you to know how to derive the fourth order Runge-Kutta method. What I'm going to show you are basically one of the most common fourth order Runge-Kutta method, also commonly known as the RK4 method, without showing you the derivation. Okay, but you should know how the second order Runge-Kutta method is derived, which basically reduces to the midpoint and Hume's method. So for the RK4 or the fourth order Runge-Kutta method, you can write it in this general form over here, and this is one of the most common RK4 techniques that is being used to solve first order ODE. So assuming that we are at the current step I, in order to find the unknown at I plus 1, you are going to take the value of y at the current step and you add it with h over 6 times k1 plus 2k2 plus 2k3 plus k4. So what are these k1 to k4? These k1 to k4 are essentially just different values of f evaluated at different points. So for example, k1 is given by f that is evaluated at ti and yi. K2 would be the f evaluated at ti plus h over 2, which is at a half time step, and you have yi plus k1 h over 2. So for k3 you have its own expression, for k4 you have its own expression as well. Okay, and if you look at this equation, what essentially we are doing here is k1 is just f at ti yi. If you recall, this has a similar form as the Euler method, meaning that this is the slope at the current step. And then you have k2, which is at the half step, you have k3 also at the half step, and you have k4 at the next step. So what we are doing here essentially is, with the RK4 method, we are trying to get a weighted average of the slope at different points in order for us to predict what is going on at y at ti plus h. Okay, so this is essentially captured by what you have over here. So by using different combinations of slope, we are able to improve the accuracy of our numerical solution. For Euler method, we only use the slope at the current point. For Hume's and midpoint method, we take the average of the slope, or we take the slope either at the midpoint, or we take the average of the slope at the current point and the next point. The RK4 method is very accurate because it takes a linear combination or weighted combination of the slope at different points. Okay, so with RK4 method, you wouldn't need to know how the RK4 method is derived. You need to know how the RK4 method is actually calculated. So if you look at the handwritten notes that has been uploaded into Moodle, there's this example here. I don't want to spend the time in this recorded lecture to go through this example. I would advise you to look at it from the printed notes or the handwritten notes and try to understand how the RK4 method is being implemented.